As endo and exothermic processes occur, whether they're physical or chemical changes, one of the key ideas that we're talking about with the transfer of energy is a concept of thermal equilibrium. Thermal equilibrium is a fancy way of just saying they're at the same temperature or that the average kinetic energy of the particles is the same. The graph right here, a Maxwell-Boltzmann distribution, which is covered in other topics, kinetics, gas motion, etc., shows us this average kinetic energy or the speed of the particles versus the number of molecules. And as something is hotter or colder, we would see a slight change there. One thing that's important is no matter how hot or how cold our sample is, we're still going to have a spread of particles. There might be some that are moving slowly. There'll be some that are moving very fast, but most of them are moving kind of in this middle area. When something is heating up or increasing in temperature or gaining heat, all synonyms, we would think about the particles on average speeding up, not necessarily all having the exact same speed, but it is appropriate and correct to say that they're moving faster. When something cools, the particles are decreasing in kinetic energy. There's still a few that might be moving fast, but many of them are slowing down. And when we're thinking about that, there's all sorts of statistical things we could look at. We've got average speed, root mean square speed, and most probable speed. But really, we just need to understand that we're talking about the speed of the particles being tied to the speed or the temperature. And as something heats up, it is heating up because energy is being transferred to it. That is happening in the form of heat, or it's happening because the particles are being collided into by faster moving particles. That causes the fast particles to slow down, the slow particles to speed up, and the heat to be transferred. That process never goes in reverse. You can't have a fast moving particle hit a slow one, and then that guy slow down and the fast guy go even faster. Although we could do calculations that would support that as a possibility, it just never happens. And there's even a full conceptual kind of challenge with that called Maxwell's demon, going back to the Maxwell-Boltzmann distribution here, trying to figure out how or why that could happen. But all of this comes to the idea that we're speeding up, we're slowing down until the kinetic energy of the two systems reach thermal equilibrium or reach the same average kinetic energy. Once again, we don't have all the particles moving at the exact same speed. And an important piece of that is that mass is a part of average kinetic energy. But whether we're talking about a gas, a liquid, or a solid, if they're all at the same temperature, we would know that they're all at the same average kinetic energy. That would let us to know certain things about the particle speeds if we knew about the masses, but we would also recognize that when they are at the same speed, there is no net transfer of heat, or although one particle might speed up, it would accompany another one slowing down. Things heat up and cool down until they're at that same temperature.